look at is when we have a question where we're just told we have an imaginary root. Not as helpful as the last one, is it? Because it's not as inclusive of information. But this one's actually simpler.
Is this the second example?
Yep, second example. If we have a single imaginary root, how many roots does it tell us we have?
2.
2. There's going to be at least 2. If, alright, suppose, given p of x has a purely imaginary root, then suppose that the root is going to be, what is it then? Root, whoops, a root could be bi. So that's our root there. Now, if bi is a root, then negative bi is also a root. Where b is obviously a real number. Or cool? And it's probably non-zero. Okay, now if that's the case, then we can go for sum and we can go for our product. For our sum, it's just going to be adding the 2 roots together. It's going to be bi plus negative bi. And that's going to give us 0. For the next one, it's going to be the product. It's going to be bi multiplied by negative bi. And that's going to be simply negative b squared I squared. And that will just give us b squared. Is that all right? So if we're going to factorize polynomial p of x, then p of x is going to be, in this instance, let's go, we've got a, we've got b, let's go cx plus d, and then we're going to have x squared plus 0x plus b squared. So we've got a dot situation over here. Now simply by inspection, are we able to remove some of the coefficients that have been defined to reduce that complexity?
Yeah, C could be A.
C could be A, that would be ideal. Are there any more? The less coefficients we have, the more straightforward this is going to be.
I don't know.
Okay, let's start expanding out. In fact, let's hold up a bit. Let's go the linear one here, 15. Sorry, the constant one. We're going to go db squared equals 15. So we can say that d is going to be b squared over 15. So our p of x is going to be ax plus b squared. Is that correct?
Is it not 15 on b squared?
Just checking you're watching. And you were watching, so well done. Next one, x squared plus b squared. Okay, that's much nicer. 2 unknowns, and we're going to have at least 4 equations built up. Okay, expanding this out. Brad? Question?
No.
Okay, expanding this out, what method do we have? Synthetic. So we're going to have b squared, we're going to have 0, we're going to have a 1. For our linear, it's going to be a, it's going to be 15 over b squared, and that's all going to be multiplied. Sorry, I'm not using the red here. Doing this, we're going to get 15, because the b squared's cancelled. We're going to get 0, and we're going to get 15 on b squared. We get a shift, we're going to get a b squared, we're going to get a 0, and we're going to get an a. We add them. Voila. Next, we need to be strategic. Which coefficient is probably going to be the easiest to work with first? X, because it's just a constant coefficient, and I'd probably go for this one here, because that won't give us anything, because a is a. So build our two equations. 10 is going to equal ab squared. That's equation 1. And the second one is going to be a plus 1 will give us 15 over b squared. Alright, now for the next part, what I'll typically do is I think, what's the easiest substitution here? I would want to use it on the calculator, but they're not linear, because you got that. So we can sub in this guy into here. So do you want to sub in for b squared, or do you want to sub in for a, Nick?
B squared.
You want to sub in for b squared?
No, sub in for A. Sub in for A to get B squared, man. Yeah.
Okay. Sub in for a. So a is going to be 10 over b squared.
Yeah.
So because of that, we're going to get 10 over b squared plus 1, 15 over b squared. We multiply both sides of the equation by b squared. We get 10 plus b squared equals 15. B squared is going to be 5, hence, that's not a good b. B is going to be plus or minus root 5. Is that alright?
Could you just explain to me why db squared equals 15?
Where?
Like top left and the
Back on the
left
left
bottom.
side.
Oh, here?
Yeah.
Okay. Do you see that? Where are we? Do you see the 15 here?
Yep.
This is our constant. To get the constant, we're always going to multiply the two constants in the factors. D times b squared is always going to yield the constant term. So if we go d times b squared, it will have to equal 15. And because we have that, we're able to rearrange. And the advantage is we reduce the amount of unknowns.
Yep, that makes sense.
Cool?
Yep.
Yeah, we always want to reduce before we expand, because you'll have too many unknowns. Sometimes you just have to do it, but you don't want to. You want to reduce. Alright, are we cool with that so far? So b equals plus or minus root 5. And because of that, a is going to be plus or minus root 5 over 10. Rationalize the denominator. That's going to be 5. Oh. Is that the right answer? Maybe. Okay, this is going to be 10 root 5. So that's going to be I think we've got a mistake here. Oh, sorry. Sorry, I've seen the mistake. Okay, guys, don't worry about b for now. B squared is 5. Therefore, our a is going to be 2. Hence, our factorized polynomial is going to be, it will be 2x plus d. What is d? 15 over b squared, so that's going to be 3. b squared's 5 times, over here it's going to be x squared. What was our b squared again? 5. Now we have a dots situation. How do we factorize dots?
A squared take b squared.
X it's going to be take. This will be I root 5. X take negative I root 5. Whereabouts?
At the very end.
Wow, I don't even know where that came from. Are we okay with that? So the point is, when you're told you have a purely imaginary root, all it's saying is that you won't have the real component to the root. It's just going to be something I. In this case, it will be bi and negative bi, or whatever coefficient you want to give it. Are we cool with that?
How did the 5 turn into I? Wait, how did the I even get there?
Because this is dots. Do you remember dots factorization? Difference of two squares?
How is that different?
Because you got
Wait, why are you doing that then?
Okay, if this was a minus, it would be x plus root 5 times x take root 5. Because it's a plus, we put in the I. If you expand that into that, you'll find you get that. If you don't believe me, have a go.
So you're saying if it doesn't have a first degree polynomial, it has to be dots? I don't get it.
If you have no linear term, you've got a dots case. If your linear term is 0, it's dots.
100%.
Yep.
Okay.
You can always factorize it using dots if there's no linear. Any other questions?